Okay, so we're starting to solve the kinematics problems. Our objective is still to be able to identify and list the givens in a problem while relating them to the appropriate variable. So let's start with what we have or view and then where we're going to go with it. To begin with, these are the variables that we've talked about for kinematics. The initial position, the final position, the initial velocity, final velocity, acceleration, which is the change in velocity, and the elapsed time. Notice that anything with a subscript of 0 is initial. That is the starting point for something. And think of it as a number line, and this is 0 on the number line. But we don't write this as x sub 0 or x subscript 0. Instead, we kind of use a nerdy shorthand, and we call it naught, N-A-U-G-H-T. So this is x naught and v naught, and that means initial. So we have the start, which is initial position, initial velocity, and we have the final velocity, final position, and final velocity. Notice no subscripts on the finals. They're just without a subscript, we assume it's the final. In some values, they never change, like acceleration. So it doesn't have a naught, it doesn't have a final, it doesn't have anything to it. And t is just going to be our elapsed time because we're always going to assume that our initial time is 0 for all our problems for right now. And where are we going with this? Well, we're going to use these 4 equations eventually to help solve the problems. It's going to be a pretty straightforward process once we explain these concepts and where this happens. But we have to start here with the givens on the left. Our goal is to find at least 3, and if sometimes we find 4 and will give us choices, but find as many givens as we can. You need at least 3 to use any of those equations on the right. So first step we talked about, and that's using the units as a clue. So if you have a distance unit, you know that your given is either x or x naught. If you have a time unit, it's going to be the time. If you have a distance over a time, it's one of the velocities. If it's a distance over 2 time units, it's an acceleration. So that kind of gets us set up with step 1. Now let's look for other clues for identifying the givens. For the velocity, we're going to see if the given velocity occurs at the beginning of the story or the end of the story, and that's going to help us to decide if it's v naught or v. V naught's the beginning of the story, and v by itself is the end of the story. And the story is the motion itself. So our story is defined by whatever's moving in time, the start and the finish. To help us with this, we're going to look for certain clue words to make our life simple. Like if it says stop, maybe something starts at a stop or it comes to a stop. That implies the initial velocity at the beginning of the story or the final velocity at the end of the story is equal to 0. So if it comes to a stop, the final velocity would be equal to 0. Look for the word rest. If you see the word rest, that implies that either the initial velocity is 0 or the final velocity. So a car could start from a rest, that's the beginning of the story, so the initial velocity is 0, or it could come to a rest, the final velocity is equal to 0. The word drop. Drop is a great one because when you see the word drop or you know something's dropped, it gives you a couple variables. Take a pencil, put it in your hand, hold it out shoulder height, and open your hand. You just dropped the pencil. And when you drop the pencil, the initial velocity, v naught, is equal to 0. The other way of looking at this is I didn't throw the pencil down. If I threw the pencil down, the initial velocity would be something that's not 0. And the acceleration. So the acceleration is the change in velocity. When I opened my hand, gravity pulled it out of my hand and it changed its velocity 9.8 meters per second every second it was in the air. But we don't always refer to that as the velocity change. We refer to that as the acceleration. So acceleration is how that velocity changed, 9.8 meters per second squared. And gravity always works down. Always works down. If gravity didn't always pull down, then we could have a cool time walking on the ceiling and sitting on the walls. That doesn't happen. Free fall. Free fall doesn't imply both things drop does, only half. Free fall implies that gravity is pulling an object down at 9.8 meters per second squared. Free fall means for us, right now, we're moving vertically in the air without any flight control. No parachute, no air resistance, no wings, no fins, nothing to control our flight. Gravity just pulls us down. That's what free fall is all about for us right now. Okay, so I've got all this information. Let's see how it applies in 2 example problems. We'll start with this one. My goal here is to list my givens. I'm going to list the variable, the number, the unit, a direction if it's a vector, and so we'll talk about some vectors here. And then I'm going to add one more thing is I want you to tell me why you made that decision. As we move on in kinematics, we're not going to add the last little step, but for right now, it's very important so we can see why we're making the decisions we're making, or so I can see why you're making these decisions. An angry mob lynches a physics teacher after receiving their grades. They throw the physics teacher off a tall building. They throw the physics teacher straight down with a velocity of 20 meters per second. The teacher falls for 3 seconds before landing on a stack of empty cardboard boxes. How high was he thrown from? Okay, easy ones. Let's go for the low-hanging fruit unit clues. I see 20 meters per second, so that's one of my velocities. And I see 3 seconds, so that's going to be a time. That's easy. They throw the physics teacher off a tall building. That means gravity moves the physics teacher. They give it a head start, and then gravity takes over. That's free fall because the person cannot control their flight once they're in the air and gravity is moving them. Free fall. Let's see, anything else? Oh, the question. How high was he thrown from? How high? Well, that's a displacement. So that's going to be my x variable. Now I make a list of givens. And when we say list of givens, I literally mean a vertical list, not a horizontal thing separated by commas, a vertical list. So what we'll do to communicate better in our format is we'll have a list of givens on the left, and then we'll have a lot of work on the right next to it. So let's start with our list of givens. Easy one, 3 seconds. That's going to be the time. So the time is 3 seconds. And how do I know that? Elapsed time, unit clues too. The next one, let's see, 20 meters per second. That's a velocity, but which one is that? They throw the physics teacher straight down with a velocity of 20 meters per second. The teacher falls for 3 seconds before landing on a stack of empty cardboard boxes. Oh, well, the 20 meters per second is the beginning of our story. Remember, our story is defined by the motion, so that's the initial velocity. Now, a velocity is a vector. It has magnitude and direction. So that's 20 meters per second. That's the magnitude. And the arrow is the direction. And an arrow is a lot easier than having to write the word down. You know, we're all kind of lazy there. So the arrow works great. And this is the start of the story. So 20 meters per second is the initial velocity. Okay, let's keep going. Free fall. Free fall implies that the acceleration is equal to 9.8 meters per second and a direction. Acceleration is also a velocity, so it has magnitude and direction. Magnitude, 9.8 meters per second squared. Direction, an arrow. And I know that because it's free fall after being thrown. X naught is equal to 0, always. Well, for 95% of the problems we have, we're always going to make X naught equal 0. So it's kind of a free space if you're doing bingo. I said earlier you're going to need 3 unknowns to solve anything. X naught is not one of those that you have to have because it's always going to be 0. You want one of the others. And then finally, I've got high. How high was he thrown from? So I'm looking for a displacement, so I need to know its final position. And I know that will be the displacement that the physics teacher traveled through. Your paper would look something like this. Second example problem. A baseball is rolled horizontally at 45 meters per second. The ball slows down at a rate of 5 meters per second squared. How long does the ball roll before coming to rest? Start with unit clues. Horizontally, 45 meters per second. So I've got direction, I've got magnitude. That's great, and that's velocity. Unit clues, 5 meters per second squared. That's the acceleration, so that's easy. How long does the ball roll before coming to a rest? So that's our colloquial way of saying time when we say how long does the ball roll before it comes to a rest. Oh, coming to a rest. More implied words, rest. So it comes to a rest, so that something about that's going to be the velocity is equal to 0 somewhere. So again, my list of givens. I'll start with 45 meters per second. The ball is rolled 45 meters per second, and then stuff happens to it. So that's the beginning of our story. So the initial velocity, beginning of the story, is 45 meters per second. That's magnitude. And then draw an arrow for direction. I assumed it went to the right because I live in America and we write from left to right. So we tend to assume the positive direction goes to the right, number lines go to the right, coordinate axes go to the right. It all just kind of fits. So it's going to the right. Start of the story. And what else? Next one, unit clue, 5 meters per second squared. That's the acceleration. So 5 meters per second squared. Oh, what happened here? So I wrote the arrows going backwards because it said it's slowing down. And notice I also made the number negative as well. So it's 45 meters per second and it's a negative acceleration. We don't always use the word deceleration, but often, especially now, we'll talk about the negative acceleration. That means I'm removing velocity as it rolls. And that's what the arrow tells me because it's going the opposite direction of V naught. Anytime something is going the opposite direction of another quantity, we make it negative, because that's what the negative sign actually means. It means the opposite of. Okay, what else? Oh, it comes to a rest. That's the end of our story, because it comes to a rest after doing stuff. So that means the final velocity is equal to 0 because it says it comes to a rest. That's how I knew that. X naught's equal to 0. That's always for us, or for now, 95% of the time. And then it says how long. That's time in this case. So that was our colloquial way of saying time. So that means that we're looking for this elapsed time. My paper would look something like this. Fill in a couple more here. There we go. So that's what my paper would look like.